Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture on energy balances. So, in the last lecture we looked at the procedures and objectives in which we would approach energy balance problems. During that time we actually discussed that we can calculate change in internal energy and enthalpy only for certain types of processes. Today we will look at a specific type of process where there is no phase change or reactions happening. So, we can actually have to calculate change in enthalpy for different steps during such a system. So, the first type of a process would be where pressure changes at constant temperature. Now, experiments have shown that specific internal energy is not a function of pressure for solids and liquids at a fixed temperature, and this is also true for specific volume. If pressure of a solid or a liquid changes at constant temperature, then you can assume that the change in specific internal energy for this process is equal to 0, and this is approximately equal to 0 because it is almost negligible. And you also have this change in specific enthalpy, which is the summation of the change in internal energy plus delta of P V cap. So, this can then be simplified to be V cap delta P. So, this value is usually very small because the V cap value for solids and liquids is small. So, V cap being inverse of density, for solids and liquids which have high densities, the value for V cap would be very small. So, the term would be of significance only when the pressure changes are very high. So, you can tend to ignore it in even for solids and liquids for pressure changes which are very small. For ideal gases, both U cap and H cap are independent of pressure. So, you can assume that change in specific internal energy and specific enthalpy would be 0 for ideal gases. So, if you have a gas which is undergoing an isothermal pressure change, then you would assume this to be 0 even for real gases because it is almost negligible, unless the gases are at conditions which are well below 0 degree Celsius or well above 1 atmosphere. Under these conditions, what happens is the ideality of the gases become questionable. We cannot actually assume ideal gas behavior under conditions where temperature is well below 0 and pressure is well above 1 atmosphere. So, because of this reason we would want to use these values for specific internal energy and specific enthalpy while performing energy balance calculations. However, there is no equation which can be used directly for this. You would have to use it from tabulated values which are built on experimental data. So, if gases are far from ideal behavior, or even if the real gases undergo huge changes in pressure, then you must use property tables or other thermodynamic correlations which can be used to calculate the change in specific internal energy and change in specific enthalpy. So, such thermodynamic correlations can be obtained from different thermodynamics books. This is beyond the scope of this course and we will not be discussing the thermodynamic correlations. For this course, most of the problems would have very small changes in pressure, and this is especially very valid for biological systems or even biochemical reactions where you would usually not have that significant a change in pressure. The next type of process is where you have changes in temperature. So, for these processes, when there is a constant pressure and temperature is changing, we have to account for change in internal energy and change in enthalpy. Sensible heat is the term which is used to define the heat which is actually transferred to the system to raise or lower the temperature of a substance or a mixture. So, when there is change in temperature, there is actually sensible heat which is supplied to the system. So, this heat is absorbed by the system and the temperature actually increases because of this heat supplied. The quantity of heat which is required to make a change in temperature might have to be calculated when we perform energy balances, and this is given as Q equals delta U for closed systems and Q dot equals delta H dot for open systems. So, this equation itself comes from the general energy balance equation, assuming changes in kinetic energy, potential energy and shaft work are negligible. Sensible heat can be calculated from change in internal energy or enthalpy, and this value can be directly used for understanding how much energy needs to be supplied or heat needs to be supplied to increase the temperature of a system from one point to another. Specific internal energy itself is strongly dependent on temperature. If temperature changes and system volume remains the constant, then specific internal energy depends on the temperature as shown in the figure. So, you can see that the specific internal energy increases in an exponential fashion as temperature changes. The slope of this curve as delta T tends to 0 is called as the heat capacity at a constant volume or CV. So, we have already seen this term before, and this slope which we have as a tangent for this curve would be the CV for this particular component at the given temperature. This CV is given as limit delta T tends to 0 delta U cap divided by delta T. So, which is can also be written as dou U cap dou T at constant volume. So, specific internal energy is a function of temperature, and as we saw through the curve, this particular function is not a straight line, which means CV, which is the slope of the tangent drawn to the curve, will not be a constant for different temperatures. CV itself is actually dependent on temperature, and it is given in terms of polynomials which can be obtained from textbooks and reference books. The change in U cap for a temperature rise from T to T plus dt is at constant volume can be given as du cap equals CV, which is a function of temperature, dt. So, delta U cap would be integral T1 to T2 CV dt, where CV is actually a function of temperature. So, this correlation for CV can be different for different components, and even for the same component which is in different phases, you would have different CVs. So, water liquid versus water vapor would have different CV values, and we would have to use the appropriate CV value for the chemical component and also its physical state. This equation is exact for ideal gases, and it is a very good approximation for solids and liquids while we perform calculations. It is also valid for non-ideal gases if volume is a constant. So, if you have a process where you have temperature and volume changing, then what you would do to account for calculating the change in internal energy would be you assume a hypothetical path. The first step can be where volume changes at a constant temperature, and the second step would be where temperature changes at constant volume. For the step 1, where there is only volume change and no change in temperature, delta U cap would approximately be equal to 0 because it is negligible for all substances except non-ideal gases, where there is going to be huge changes in pressure or volume and so on. For step 2, where delta U cap depends on the temperature change, you would have to calculate it using the integral equation which we just derived. Delta U cap would be integral CV dt. So, the summation of these two change in internal energies will give you the total change in internal energy for the process. Instead of a constant volume process, if you were to have a constant pressure process, then you would have to account for change in enthalpy when the substance is heated. So, enthalpy also strongly depends on temperature, and this relationship is similar to what you saw with internal energy. So, if delta H cap is the change in enthalpy for an increase in temperature from T to T plus delta T, then as delta T tends to 0, the ratio of delta H cap by delta T approaches a limiting value which is called as the heat capacity at constant pressure. So, this is similar to what we saw for the CV value. Here this is called Cp, which is the heat capacity at constant pressure. Cp is given as limit delta T tends to 0 delta H cap divided by delta T, which equals dou H cap dou T at constant pressure. So, from here we can actually calculate the value of delta H cap as integral Cp dt. Cp again is a function of temperature, just like we had for Cv. As you saw the curve for curve for specific internal energy changing with respect to temperature, this is also not a straight line, which means that the slope which would be drawn for the tangents would keep changing as the temperature changes. So therefore Cp will also be a function of temperature, and we would have to calculate it as integral Cp dt. So let us assume a process where both temperature and pressure changes. Here again we would build a hypothetical path where the first step would be change in pressure and the second step would be the change in temperature. So for the first step, delta H cap would be equal to 0 for ideal gases, and it would be equal to V cap delta P for solids and liquids. So this V cap delta P can be very small. The second step would be change in temperature. So the delta H cap value for the second step would be calculated using the integral equation which we just derived, which is integral Cp dt. For the process that we described where both pressure and temperature changes, for ideal gases and for non-ideal gases with pressure changes that are small, the equation for delta H cap, which is the total change in enthalpy, would be integral Cp dt. So the first step where pressure changes would be 0 for ideal gases and it will be negligible for non-ideal gases. For solids and liquids, the total change in enthalpy would be the summation of delta H cap 1 and delta H cap 2. So this would be V cap delta P plus integral Cp dt. V cap delta P is the enthalpy associated with the process where pressure changes at constant temperature. Usually V cap delta P is negligible compared to the other term, where because the other term would have a significant impact. However, if the pressure changes are very large, then this term would also have to be accounted for, because that could also have a significant magnitude. To calculate the value for delta H caps and delta U caps, we need to know the heat capacities. These values, which are Cp and Cv, are tabulated in handbooks and textbooks. You would be able to get the different Cp values and Cv values from different sources, and usually it is a polynomial which is written in terms of amount of energy per unit amount per unit temperature interval. So this would be joules per mole Kelvin or BTU per pound mass degree Fahrenheit. So if you remember, when we discussed temperature, I talked about the difference between a unit change in temperature versus the unit of temperature itself. So here what we actually have is a temperature interval. So what we look at as Kelvin or degree Celsius would be delta Kelvin or degree delta Celsius. So we do not use that explicitly, so we just write it as Kelvin or degree Celsius. This term is also called as the specific heat, and the heat capacities are expressed as polynomials, as I said, which would take the form Cp equals A plus Bt plus Ct square plus dt cube. So this particular polynomial represents how Cp changes with respect to temperature. So this, based on this equation, we can calculate the delta H cap values by integrating the Cp with respect to temperature. In the table, the value for A would be given as A times 10 power 3 equals some numerical value. This means that you have A times 10 power 3 equals some value. So the actual value for A which you would use in the polynomial would be the numerical value times 10 power minus 3. I will show you an example when we perform calculations, but please understand that you need to look at the table carefully and use the values appropriately. So the simple logic you should use is the value for A would always be larger than the value for B, and the value for B would be larger than the value for C, and the value for C would be larger than the value for D. Only then the impact of temperature would be accounted for correctly. Otherwise there would be an extremely high effect on temperature, effect of temperature on Cp, that your numerical values you arrive at would be completely haphazard. So you can get these values for A, B, C and D from any textbook or handbook. In many cases, the textbook or handbook would actually list only Cp values, and you might have to calculate internal energy, which means you would need Cv values. So there are simple correlations which can help you calculate Cp from Cv. So for solids and liquids, Cp is approximately equal to Cv. For ideal gases, Cp equals Cv plus R. So these are the simple correlations which you can use for calculating Cp from Cv or Cv from Cp. For non-ideal gases, the relationships are actually very complex, and you would have to use some kind of an empirical correlation which can actually be used. So, these you can get from other textbooks which would not be part of this course. If enthalpies have to be calculated very frequently, then it is useful to build a table which can be used and referred commonly. Example would be steam tables. So, the steam tables lists the values for specific internal energy, specific enthalpy and specific volume, and because of this we can use it regularly, and steam being a common component in any chemical or biochemical process, it is useful to have this kind of a steam table. Similar tables have been built for combustion reaction gases. So, gases like carbon dioxide, carbon monoxide and water vapor and so on, which take part in the combustion reactions, have also been tabulated. So, such tables are available in the textbooks prescribed and also in other handbooks. So, what you need to be careful about is whenever you are using such tables, you need to use appropriate reference dates. In the last lecture, when we talked about objectives and procedures, I also talked about identifying appropriate reference dates. So, identifying appropriate reference dates would mean that when you are using tabulated data, the reference state used should also be the reference state which is shown in the table. So, here is a simple example problem which will help us understand how to calculate change in specific internal energy and specific enthalpy. Assuming ideal gas behavior, calculate the heat that must be transferred in each of the following cases. A stream of nitrogen flowing at a rate of 100 moles per minute is heated from 20 degrees Celsius to 100 degrees Celsius. Nitrogen contained at the second process is nitrogen contained in a 5 liter flask at initial pressure of 3 bar being cooled from 90 degrees Celsius to 30 degrees Celsius. So, the first process is where nitrogen is flowing and you are heating it from 20 to 100 degrees Celsius. The other one is in a closed system where you have a 5 liter flask and there is an initial pressure of 3 bar given, and the process is a cooling process from 90 to 30 degrees Celsius. Let us see how to solve this problem. For the first process, where heating of 100 moles per minute of nitrogen is happening, you have an open system. The general energy balance equation would use enthalpy. So, you would have the general equation as Q dot equals delta H dot. So, this is based on the assumption that there is no change in kinetic energy or potential energy and there is no shaft work. So, here the system does not have any moving parts, and you also have that there is no change in velocity or change in position given. So, we can assume these things and we would end up with Q dot equals delta H dot. So, what we need to do is calculate delta H dot. So, delta H dot would be equal to n dot times integral Cp dt. So, we now have to identify the Cp values which are given in the textbooks. So, the Cp value given for nitrogen is 0.029 plus 0.2199 times 10 power minus 5 T plus 0.5723 times 10 power minus 8 T squared minus 2.871 times 10 power minus 12 T cube. So, integrating this equation we can actually get delta H cap. Delta H cap would be integral Cp dt. So, integrating this with respect to the temperature given from heating from 20 degrees Celsius to 100 degrees Celsius, we would be able to get the value for delta H cap. So, when we do this, we get delta H cap equals 2.332 kilojoules per mole. So, now we need to calculate delta H dot, which is equal to n dot times delta H cap, which is 100 times 2.332, giving you 233.2 kilojoules per minute. Now, this is the heat which needs to be transferred also. Q dot equals delta H dot, which is 233.2 kilojoules per minute. So, this is the simple calculation that needs to be done to calculate the amount of heat that needs to be transferred for this process where nitrogen is being heated from 20 degrees Celsius to 100 degrees Celsius. So, the next process is a 5 liter nitrogen flask is at an initial pressure of 3 bar is cooled from 90 degrees Celsius to 30 degrees Celsius. So, this would be a closed system and it is a constant volume system. So, you have Q equals delta U. So, now you have to calculate delta U. Delta U would be equal to N delta U cap. So, we need to know the values for N and delta U cap. So, delta U cap can be calculated as integral Cv dt. So, Cv can be calculated from the Cp value which we had. Cv would be equal to Cp minus R, because we know the correlation for Cp and Cv for an ideal gas. So, now we can, from this we can actually calculate the value for Cv as Cp, which is 0.02900 plus 0.2199 times 10 power minus 5 T plus 0.5723 times 10 power minus 8 T squared minus 2.871 times 10 power minus 12 T cube minus R. So, using the R with the appropriate units, you would have R value as 0.008314. So, which is kilojoules per mole degree Celsius, that is the units for Cv used. So, we would have to use the same units and we would be having this value as 0.02069 plus 0.2199 times 10 power minus 5 T plus 0.5723 times 10 power minus 8 T squared minus 2.871 times 10 power minus 12 T cube. So, performing integral Cv dt, we can get delta U cap as minus 1.25 kilojoules per mole. So, the initial temperature is 90 degrees Celsius and the final temperature is 30 degrees Celsius. So, within this limits we have integrated it to get minus 1.25 kilojoules per mole. As the process is a cooling process, the change in internal energy is negative. Now, we need to know the value for N. N is the number of moles. So, using ideal gas law, we can calculate N as PV by RT. So, which would be 3 bar times 5 liters. So, this divided by the temperature, which is 363 Kelvin, which is the initial temperature of 90 degrees Celsius, and the R value with in terms of bar and liters and Kelvin would be 0.08314 and the units would be liter bar divided by mole Kelvin. So, cancelling out the appropriate units, you would get the number of moles as 0.497 moles. So, from here we can calculate delta U or Q. Q would be equal to delta U, which is equal to N delta U cap, which is equal to minus 0.621 kilojoules. So, this is the amount of heat that needs to be removed to cool nitrogen in a 5 liter flask at an initial pressure of 3 bar from 90 degrees Celsius to 30 degrees Celsius. So, with this we have looked at two simple processes where we have calculated change in enthalpy and change in internal energy using Cp and Cv values. In both these processes, we had the luxury of having the value for Cp given to us. In some cases, Cp values or Cv values are not readily available. This is especially true in biochemical processes or in biological processes where the components which we are using are unique and we might not actually have the exact value of Cp which is measured. So, this polynomial expression which is used is actually based on experimental data, and this cannot be exhaustive for all the possible compounds and elements which are present in the nature. So, if tabulated formula does not exist, we need to look at some approximation techniques which would help us estimate the Cp or Cv values, and we can use them appropriately for performing calculations. One such method is Kopp's rule. This is a simple simple empirical method which is used for estimating heat capacity of solids and liquids at around 20 degrees Celsius. So, the logic here is each element in the compound has a particular contribution towards the Cp value, and depending on the number of atoms of the element, we multiply it with the individual contributions, and the summation of all the contributions by individual elements gives us an approximate Cp value. So, this approximation is a very simplistic approach. There are much more accurate techniques that are available, which can be seen in thermodynamics textbooks and handbooks. So, we will not go into great detail of how to use these. So, the Kopp's rule is a very handy thing to use and a very simple thing to use, that is the only reason you are being introduced to it. You can actually look up the textbooks to find what would be the contributions for the individual elements which are involved in the compound. In addition to this, we might also have mixtures. So, where we might have to calculate the heat capacity of the mixtures. The rule 1 for the gases and liquids is you can calculate the total enthalpy change as the summation of the enthalpy changes of the pure mixture components. So, this means that you are ignoring the enthalpy associated with mixing. This is a good approximation for gases and for similar liquids. For example, ethanol and methanol being mixed, these are similar liquids. So, it does not matter, we do not have to account for the heat associated with or mixing. If it is a process like mixing of water and sulfuric acid, these are very dissimilar liquids. In that case, we would have to account for the heat of mixing or the enthalpy of mixing. So, that is when it becomes a poor approximation to use. So, when you do this kind of an approximation where you are calculating the total change in enthalpy as the summation of the enthalpies associated with individual components in the mixture, you are basically implicitly calculating a Cp of the mixture. So, this Cp of the mixture would actually be equal to the mole fraction of the particular component times this Cp of that component and a summation of all the terms which would exist in this system. So, delta H cap would be equal to integral Cp mixture dt. So, this is what we do implicitly. We could also explicitly calculate the value for Cp of the mixture and still perform these calculations. For highly dilute solutions or gases, solutions of solids or gases, you can actually neglect the effect of the solute which is dispersed in the liquid, and we can use the Cp or Cv value of the liquid itself. This is a very good approximation only for very dilute solutions. Here is another simple example problem which helps us understand how we inherently calculate Cp of the mixture and how we could actually explicitly do that as well. You are asked to calculate the heat required to bring 150 moles per hour of a stream containing 60% ethane and 40% propane from 0 degree Celsius to 400 degrees Celsius. Determine a heat capacity for the mixture as part of the problem solution. So, what we would usually do is we would calculate the change in enthalpy for ethane and calculate the change in enthalpy for propane and add these two values to calculate the total change in enthalpy of the mixture. So, instead we could also calculate the Cp of the mixture using the mole fractions given and use that Cp of the mixture to get the final value for enthalpy. So, I will only solve the technique where we calculate the Cp of the mixture. I suggest you perform the calculations for the individual enthalpy changes and the summation and compare it against the numerical values which I will be arriving at. To calculate Cp of the mixture, we first need to know the Cp of ethane and propane. So, Cp of ethane C2H6 is given as 0.04937 plus 13.92 times 10 power minus 5 T minus 5.816 times 10 power minus 8 T squared plus 7.280 times 10 power minus 12 T cube. Cp of propane is 0.06803 plus 22.59 times 10 power minus 5 T minus 13.11 times 10 power minus 8 t squared plus 31.71 times 10 power minus 12 t cube. So, these values I have taken from your textbook, you could also get these from other handbooks. So, now that you have these two Cp values, you can calculate the Cp of the mixture. The Cp of the mixture would basically be the mole fraction of C2H6 times Cp of C2H6 plus mole fraction of C3H8 times the Cp value of C3H8. So, this would be Cp of mixture equals 0.6 times Cp of C2H6 plus 0.4 times Cp of C3H8. So, calculating this, we can get Cp of mixture as 0.05683 plus 17.39 times 10 power minus 5 t minus 8.734 times 10 power minus 8 t squared plus 17.05 times 10 power minus 12 t cube. Now that we have the Cp of the mixture, the delta H cap value can be calculated as integral Cp of the mixture dt, and the change in temperature is from 0 degree Celsius to 400 degree Celsius. So, delta H cap after the integration would be 34.89 kilojoules per mole. So, one thing you should be careful about the temperatures you use is the temperatures you use should be in the same units as the temperatures given temperature units of the Cp term. Because you have higher degree polynomials, the integration would lead to an error if you use Celsius instead of Kelvin or Kelvin instead of Celsius. So, from the equation for open system, we would have q dot equals delta H dot, which is equal to n dot times delta H cap. So, n dot here is 150, so which would be 150 times 34.89, giving q dot is equal to 5230 kilojoules per hour. So, this would be the heat required for the process. So, with this we have looked at some of the fundamentals required for performing energy balance calculations in systems where there is no phase change or reaction. So, we will look at real processes where we can have such energy balances, and we will perform more calculations. We will look at how to perform these calculations in the next class. Until then, thank you.